Now I'm going to talk about Otsu's method for thresholding, which is one of the most popular thresholding methods, probably because it's relatively simple in its implementation than the method of model fitting I talked about in a previous video. Now, to understand what Otsu says, we have first to see what are his assumptions. So he has two main assumptions that are kind of related with each other because one assumption implies the other. So the first is homogeneity. So he assumes that the two classes must be as homogeneous as possible. Homogeneous. The second is that he assumes that the two classes must be in contrast between each other. So the second assumption is contrast. And this in some cases is valid. For example, the case of this pen with this paper. So just calculate the standard deviation of, or the variance of the paper and the variance of the pixels pen. You would find that they are very, very small as compared with any other region you would take. The variance of any other region you would take in the image. Also, because this pen is in contrast with that paper, you would find that the mean of pixels of that pen are far away from the mean, from the general mean of the image. And the same thing is true for the mean of this paper. It would be as far as possible from the mean of the entire image. Now we need to describe that mathematically. So in order to get a class that is as homogeneous as possible, we have to work on the variance, the within class variance, the variance of a given class. So we have to minimize the within class variance. And the within class variance is just a measure of the variances in the two classes, okay? And if we minimize that, we would get two classes that have the minimum combination of variance. For the contrast, we need to maximize the between class variance. Okay, and the between class variance is a measure that a parameter that measures how far is the means of the two classes from the general mean of the image. Okay, so now first, one interesting thing is that the general variance of the image, and let me denote that as G, is equal to the within class variance plus the between class variance. And this, of course, depends upon the threshold. This one also depends upon the threshold, but this one does not depend upon the threshold. It is independent of the threshold. It is always constant for as long as the image does not change. Okay, so first of all, let me give you the formulas of these two parameters. So the first, the within class variance, is given by just the variance of the first class, okay, plus the variance of the second class, and we must bear in mind the proportion of the pixels of each class. The same thing here for the between class variance. As I said, it's just the distance from the general mean. Okay, and if you want to know more about the between class variance and why it works in the case of in some cases, of course, why Otsu chose that to maximize that parameter. I recommend you to go and see something about ANOVA. So ANOVA is a statistical technique. It stands for analysis of variance, and it's a statistical technique that tries to see if there are any samples in our data set that have some unique properties. Okay, and it does so just by analyzing the means of each sample. And if these means are far away from the general mean, then we must start to suspect that there is something interesting about these samples. Maybe they have some unique properties, and this means that they are just classes. Okay, and this is the case just because the mean of a given sample has to be very close from the mean of the entire population. So these are things that are known in statistics. If you want to know more, I recommend you to go and see ANOVA, analysis of variance. Okay, so let me get back to the between class variance. So the between class variance is written as proportion of the first class multiplied by the difference, as I said, between the mean of the first class minus the general mean, square that, plus the proportion of the second class by the mean of the second class minus the general mean, square that. And the reason why we consider proportions here and here is because these parameters, or these metrics, variance and means, become less relevant when the number of samples, or the size of the sample, in our case the size of the class, is small. Therefore we give it a small weight because it becomes less relevant. Okay, so it is necessary to introduce that weight for the method to work properly. So what we need to do now is either increase the between class variance or decrease the within class variance. And the reason is, if I increase the between class variance, this would imply automatically a decrease in the within class variance to compensate for that increase. Okay, and why a compensation the reason why a compensation takes place is because this term here is constant. Remember, this term is constant. So if I increase this, if this increases, this has to decrease for this fact to be valid. Okay, this is the reason why. It's like hitting two birds with the same rock. Increasing one automatically decreases the other, and this is exactly what we want to do: homogeneity and contrast between objects. Okay, so now generally what we do is we try to increase the between class variance. So we do so by considering all the possible thresholds, okay, for an 8-bit image. For example, we would have 255 or 256 possible thresholds from 0 to 255, and for each of these levels we calculate the between class variance, and we get something that is called a cost function. Okay, so this is a cost function. This is just a name for that function, cost function. In statistics or machine learning, a cost function is just some function that we want to maximize or minimize. Okay, anything we want to maximize or minimize is called a cost function in statistics. So here, when we do that for all possible values of the all possibilities of the threshold, we go to the maximum. and we get that. We take that as the optimal threshold. This is the optimal threshold, and this is associated with the maximum value of the between class variance. Okay, and this exact optimal threshold would be associated with the minimum value of the within class variance. The within class variance, as I said, because increasing this implies decreasing this. Okay, so this is how we identify the optimal threshold for in the case of Otsu's method. However, it still has its drawbacks, and the first drawback is caused by something I already mentioned in a previous video, which is when the object or when a given class represents a very small percentage in the image, and this is associated with a histogram like this one. Okay, so the optimal threshold is supposed to be somewhere here, and this proportion here is very, very small. Okay, very, very small, and this causes a fail. And kind of an intuition of why that fails in the case of Otsu's method is because the between class variance is directly associated with proportions. Okay, and when we have a very small percentage, then this introduces a very small value for a given proportion, either this one and this one, and this decreases the chance for that parameter to be maximized. Okay, so this is kind of an intuition why this fails. Other cases where Otsu's method fails is just when the assumption, usually an algorithm fails when its assumptions are not valid. For example, the assumption of Otsu is that homogeneity and contrast imply a bimodal distribution. Okay, and when this assumption is not valid, then the algorithm will break. And examples of when this is not valid is when the illumination is not uniform. This is already mentioned. We have an illumination that, for example, is very strong on the right, but very, very poor on the other side. So this causes the histogram not to be bimodal. Another case where the assumption is violated is just when the object is not homogeneous. Because remember, Otsu assumes that the object is homogeneous, but when we have an object that is not homogeneous, like this one, when it is put on a white paper, so we are gonna get problems, just because this part of the pen here is white and this background is white, so there is no contrast between the background and the object, of course, at just a particular region, which is this part of the pen. And this pen is also not homogeneous because it has black color here and white color here. So likely what we are gonna get with Otsu's method is just detecting the cap and the writing on this pen as an object, and also this part here, but the rest of the body would be classified as a background, which is in this case false.